How do we assess whether a study result is important? Let's define what I mean by importance. Importance is the importance that a relationship or study result has in the real world. Now, very similar terms that mean essentially the same thing, are practical importance, practical significance, substantive significance, and clinical significance. Importance is not the same thing as statistical significance. Statistical significance is, in essence, the likelihood that a result is due to chance alone. So that when a result is statistically significant, it is unlikely to be due to chance alone. That's not the same thing as importance. It's important to see that a result can be statistically significant and unimportant. Probably none of you know what tiddlywinks. When I was a kid in the 1950s, people still played tiddlywinks. It was a game that was associated with idling away one's time. It's kind of a lazy game that you could play and sit back and enjoy doing so. Now, suppose that I carry out a study and I find a method that improves tiddlywinks scores greatly. And indeed, we'll find that my method is better to a statistically significant degree. The improvement in tiddlywinks in my method is unlikely to be due to chance. So there's our statistically significant result. Let's assess the importance of this result for social work practice. Well, frankly, I cannot see any. So there is an example of a result that is statistically significant and unimportant. Well, is it possible for a result to be not statistically significant, but even so important? Let's look at this example. Let's say that we carry out a large-scale, well-organized, randomized trial, and that we find no statistically significant differences in outcomes in delinquency, school performance, behavior problems, and self-esteem for at-risk youth who were randomly assigned to be served in their own homes versus randomly assigned to being served in an out-of-home placement setting. So the kids randomly assigned to placement and the kids randomly assigned to own home services have similar results, similar outcomes. Now, this study is an example of a study in which several results are not statistically significant. Yet this study does indeed have important practice implications. From a public policy perspective, we much prefer to serve youth in their own families. So this large-scale study that demonstrates that kids served in their own home have, in essence, equivalent outcomes those served at placement. This is an important study potentially for guiding practice. So here then is a study with results that are not statistically significant, but that are important. In sum, it's very important that you keep statistical significance and importance as distinct concepts. The end of chapter 24 in the text builds a balanced model for data interpretation. And there are 5 key parts to this model. And the key to this model is recognizing that each of these 5 points is a separate and distinct part of data interpretation. So it's important that you don't blur these together in your own mind. And, you know, in particular what happens is in data misinterpretation is that students read that a result is statistically significant And based on that, they conclude that the result is a strong one, that the result is a causal one, that it's generalizable to many different settings, and that it's important. So they've taken the meaning of statistical significance, whether a relationship or result is likely to be due to chance, and inappropriately extended it to other parts of data interpretation. But let's quickly summarize the 5 parts of the model. Statistical significance, whether a result is likely to be due to chance. Size of association, the degree to which the values of one variable vary, differ, or change according to those of the other. Causality, whether one variable causes another. Generalizability, the degree to which a similar study result will be found in a different context. And 5, the real-world implications of the result. So, key to balanced data interpretation is to give some weight to each of these and to recognize that each is a distinct concept. I want to note that in some studies there's no attempt made at all to assess causality. For instance, many surveys have a purely descriptive purpose. So in some studies the issue of causality doesn't even come up, and in such a situation just simply have a 4-part model in your mind, one in which causality is dropped from the model. As a general rule, I do think that this is a good ordering for how your thinking might progress. 5 steps make good chronological sense. I will mention that there is a link, I think, between points 1 and 3, and that link is this, that if a result is not statistically significant, that result may well be due to chance. If the result may well be due to chance alone, in essence, you don't bother to think about causality. Canons of science want us to go with the simplest possible explanation, and if chance alone explains the result, then we're not going to consider causality. I'll just make a couple of comments on what's driving some of the different parts of the model. So, a lot of statistical significance is whether the result is likely to be due to chance, and do recognize that issues of power come into play here, and recognize that you have a greater likelihood of obtaining a statistically significant result with a larger sample than with a smaller one. Size of association covered in the first half of our course, and students and indeed textbooks often forget about size of association. And in a couple of our videos we demonstrated that it is indeed possible to have a fairly large association that does not achieve statistical significance. So that would be most likely to occur when sample size is very small. Or on the other hand, it's possible to have a statistically significant result, one that's unlikely to be due to chance, but have that result or relationship convey only very weak association. So for instance, we had an example of a study of academic achievement, or really, I guess, scores on an academic skills test, and there was a statistically significant difference between girls and boys. The girls did better, and that difference was not likely to be due to chance. The sample size was in the hundreds of thousands, and it was the case that the size of the difference was absolutely tiny. So there's an example of a statistically significant result, but where the result is trivial. And now, of course, the big factor that's driving causality is the assignment process. And in particular, when we've got random assignment to groups, that's by far the strongest design for being able to draw causal conclusions. So the random assignment removes confounding variables. In chapters 10 and 11, we looked at designs that don't use random assignment, and we asked, well, how do we assess causality in those situations? And that's where we got into the logic of controlling for potential confounding variables and seeing whether or not associations maintained as we controlled for those variables. And indeed, the multivariate statistical techniques in chapter 23 are often used to address causal issues, but the random assignment is the key. Generalizability. Now, a big factor affecting generalizability is the sampling process. I mean, when you indeed have a study sample that is drawn randomly from a large population, then you can use statistical logic to make quite confident generalizations to that population. But of course, the problem is that in so many situations we don't have large populations from which we've randomly selected, and in some situations there's no real population at all. And there, the logic of similarity in conjunction with replication is how we make cautious statements about generalizability. Finally, we've had a couple of examples demonstrating that importance is distinct from statistical significance. So all of these 5 parts rest on their own accord. I'll make another statement which is, I mean, look at the reasoning that's involved in these parts of the model. For statistical significance and size of association, I mean, our reasoning is statistical. It's entirely data-driven. Reasoning begins to get more qualitative as we move to issues pertaining to causality, so that experts would disagree, for instance, about whether some given designs let you draw strong causal conclusions. There's agreement about randomized designs that these are the strongest, but there are other designs on which the assessment of causality can be quite tricky. So as we get to generalizability, well, the statistical generalizability is quantitative reasoning. But as you go beyond the study context to non-statistical generalizability, well, there's a great deal of subjective judgment involved. It's much more qualitative reasoning than quantitative. And finally, the assessment of the importance of the study result is qualitative. It's ultimately judgment. So as we go step by step through the 5 model steps, we're moving from quantitative reasoning to more qualitative reasoning. So in sum, don't muddle these distinct parts of the model together. Keep these different parts distinct, and you'll do well. And even if statistical significance may ultimately be the key or most important part of the model, don't make it the only part. Comprehensive assessment of data requires that you look at each of these 5 points. And we're done. That's the final video. We've made it through 24 chapters. Hooray!